when it comes to the mechanism of nucleophilic substitution, from the very name, you realize it would be a reaction of this kind. Some RH with a nucleophile is forming an RNU plus X minus. So basically, a nucleophile attaching itself to the carbon chain, aliphatic or aromatic, and this X minus being replaced. एक nucleophile आ रहा है, X minus जा रहा है. You call it substitution. Carried by nucleophile, so you call it nucleophilic substitution. Now, RH halides happen to be the ideal substrate for substitution and elimination, because I might have told you in the past that X minus, they happen to be the best leaving groups. They happen to be the best leaving groups again because they are the weakest bases, and again because this HX, where you understand HI, HCl, HBr, they are very strong acids. They are very strong acids. So very strong acids would give you I minus, Br minus, Cl minus as very poor bases or very weak bases. And I must have told you umpteen times, leaving tendency is kind of inversely proportional to basicity. So all of this we have done in the past. Base का काम होता है lone pair donate करना, lone pair use करना. A base uses lone pair use करता है, you want more electron density. A leaving group comes out with its pair of electrons. So basically what's happening is, if this X is coming out as X minus, if it's a good leaving group, the process is facilitated. Yes or no? बच्चे लोग हाँ ना बोलो. Now this is the first topic of class 12 organic chemistry. Haloalkane, haloarine, which is also called alkyl halides, aryl halides. Although alkyl halides, aryl halides over aliphatic carbon and aromatic carbon is going to be two different chemistry altogether. We'll see aromatic towards the end. We'll begin with aliphatic. And in aliphatic chemistry, nucleophilic substitution is generally represented with a symbol like this. So, way back in isomerism, CIP rules, CAN, Ingold, Trilog, I would have told you these names. Now, basically, sorry? So, getting back to it, I think this part is understood. Halides are going to be ideal substrate for substitution because halides are very good leaving groups. They are very good leaving groups because they are poor bases. A strong base is a poor leaving group. A poor base is a good leaving group. And a strong acid will have a poor conjugate base. Yes or no? So because HBr, HCl, HF happens to be the strongest acid, halogen acids are the strongest acids, halides are among the poorest bases and the best leaving groups. If they are the best leaving groups, they are ideal substrate for substitution and elimination. Asmit, I think you can hear me loud and clear. Asmit, khana bolte raho.
हाँ sir.
Now yet again, before I talk more about substitution, I minus, Br minus, Cl minus, this will also be the order of leaving tendency. And this also happens to be the ease of breaking these bonds. So somewhere down the line, we'll conclude that this will be the order of reactivity. In general among iodides, bromides, and chlorides. Iodide more than bromide more than chloride will be the order of leaving nature. Even in HI, HBr, HCl, I think you understand, this will be the order of acidity. HI would be the strongest hydrocide. So I minus would be the weakest base, and the weakest base would be the best leaving group. So from the standpoint of being the best leaving group, as well as more bond energy, more bond length will mean less bond energy. So on both fronts, iodide would be the most reactive. And we'll want to move on. I was talking about CIP rules. So this British or English physical chemist, Ingold, and his colleagues, they are responsible for the coinage of these terms. Sn, where N in the subscript stands for nucleophilic, S stands for substitution, nucleophilic substitution. And I think some of you would have known by now, it's such an important part of our reaction mechanism and organic chemistry in general, that this nucleophilic substitution could take up two possible mechanisms. The two very popular mechanisms are kinetically differentiated. Suppose I tell you about a nucleophilic substitution which looks like this following. This is tertiary butyl chloride. So you have CH3, 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 Cl. This with OH minus is producing the corresponding alcohol. Cl minus is obviously being knocked out or substituted. And I propose the mechanism or the process has a rate kinetics or rate law expression, rate proportional to this RCl only, this to the power 1, and with the nucleophile OH minus, it's to the power 0. So situation like this, where I repeat, the mechanism and everything is going to owe its source to kinetic studies. Way back in kinetics, I tell you, this is rate law expression. Rate law expression would help you in proposing a mechanism or understanding the mechanism of several reactions. Naturally, out here I find order with respect to nucleophile being 0. Order with respect to nucleophile being 0 का मतलब होता है कि न्यूक्लियोफाइल का कंसेंट्रेशन चेंज करने से न्यूक्लियोफाइल का कंसेंट्रेशन चेंज करने से रेट में कोई फर्क नहीं पड़ता. इसका कंसेंट्रेशन डबल करोगे रेट डबल हो जाएगा. तो हैलाइड के साथ में सबस्ट्रेट के साथ में ऑर्डर 1 है, न्यूक्लियोफाइल के साथ में ऑर्डर 0 है. यहां पर ना we will take molecularity and order to be synonymous. Although when I tell you law of mass action, I do tell you about the difference between order and molecularity. So you remember order is something which is experimentally obtained and molecularity is something which is the sum of the stoichiometric coefficients. So in physical chemistry, I talk about the difference between molecularity and order. I think everybody is getting me. Right now, we'll believe order and molecularity are synonymous. Order 1 है, and the process where the chemical process will have the corresponding rate kinetics. Being unimolecular, you will want to represent it with a Sn1. So Sn1 would mean a nucleophilic substitution where rate kinetics is suggesting order or molecularity 1, where it's independent of the concentration of the nucleophile. So basically, this is like R is equal to K, Rx only, order with respect to the nucleophile is 0. Another classical case is suppose if you talk about the hydrolysis of methyl chloride. Now, in a process of this kind, if you have the rate of the process proportional to the concentration of halide or Rx to the power 1 and OH minus or nucleophile to the power 1, now naturally this will look bimolecular. So you understand what's happening here. When it's bimolecular, the rate will depend upon both the concentration of halide as well as the nucleophile. और ऐसा ही होना चाहिए, ideally ऐसा ही होना चाहिए, दोनों के ऊपर में rate depend करेगा. And this being bimolecular, it will be designated a symbol Sn2. Now these are the two most popular mechanisms, two popular pathways which is going to happen. एरोमेटिक में हम लोग उसका नाम ARSN लिखेंगे. यहाँ पर सिर्फ SN लिख रहे हैं, मतलब ये टॉकिंग अबाउट एलिफैटिक न्यूक्लियोफिलिक सब्स्टिट्यूशन ओनली. Aromatic, will come to it when the time is right. We'll talk about aromatic much later. This is going to be a longer journey. This is going to account for so many reactions in our syllabus, but I think I've made it very clear. Nucleophilic substitution, the two popular mechanisms, which are represented as Sn1, Sn2, are right away going to come out of the chemical studies, the kinetic studies, the kinetic studies. So what does Sn1 mean? Sn1 means a process where the rate of the process is independent of the concentration, and later you will find also the nature of the nucleophile. And Sn2 bimolecular would be more expected. So I think I have made Sn1, Sn2 and these terminologies clear to you. Naturally, the terminologies and even the mechanism proposed, I repeat, would come out of kinetic studies. you know, you would have known a little bit of this in kinetics, or you know, the beginning of equilibrium, which I tell you, it's experimentally done. इसका कंसंट्रेशन चेंज करने से रेट चेंज होता है, इसका कंसंट्रेशन चेंज करने से रेट चेंज नहीं होता है, मतलब Sn1 है। और जिस प्रोसेस में रेट दोनों के कंसंट्रेशन पे डिपेंड करता है, वो बाई मॉलिक्यूलर है, वो Sn2। ठीक है। Now when it's Sn1, where it's independent of the concentration of nucleophile, please hear me out. There are only two cases. There are only two cases where a particular reactant does not feature in the rate law expression. You know, this is called the rate law expression. The basic fundamental theory of chemical reactions is the theory of collision. So many times in a textbook you will find reactants collide, and all the successful collisions, they mature into products. So that's a basic, fundamental, old approach to chemical reactions, that the reactant molecules will collide, and all the successful collisions, they'll mature to products. All right. And naturally, with increase in concentration, the probability and the frequency of collision is bound to increase. So that is why we believe increase in the amount of the reactants is always going to favor the forward reaction or the rate of the process. So every time a reactant does not feature in the rate law expression, I tell you there are only two possibilities. One, अगर वो excess में है तो मान लो एक प्रोसेस है जहां पे वाटर रिएक्टेंट है और मीडियम भी वाटर है, इथेनॉलिक न्यूक्लियोफाइल काम कर रहा है, मीडियम भी इथेनॉलिक है। So you understand when you have something acting as the reactant as well as the medium, you can't talk about change of its concentration because you have too much of it. So that is one case where you have an excess of a reactant, then you say that it's going to be not featuring in the rate law expression. To rule that out, you will want to conduct experiments, say at lower concentrations of OH minus. And at lower concentration of OH minus, even on those fronts with lower concentration, if the rate is independent of OH minus, this means that factor is evened out. एक्सेस वाला बात तो नहीं। एक कारण हो सकता है कि कोई रिएक्टेंट रेट लाw expression में नहीं है अगर वो एक्सेस में है। All right, so we are ruling that out. We are working at low concentrations of OH. All right, what is the second possibility? The second possibility is if that reactant is not involved in the slow step. I've spoken about slow step. I've called this slow step as the rate determining step. And I did tell you that everything which speeds up the slowest step, everything which helps or aids the slow step, would eventually affect the rate of the process. I think you're understanding me. So I think this possibility is going to be, give me the mechanism of Sn1, where if the nucleophile is not there in the rate law expression, इसका मतलब है कि न्यूक्लियोफाइल स्लो स्टेप में काम नहीं करता। इसका मतलब न्यूक्लियोफाइल स्लो स्टेप में काम नहीं करता। You getting me? I must have told you about rate determining step in the past. You remember me drawing a set of vessels, and the smallest interconnector was eventually giving you the rate of the outflow of sand. अरे हाँ ना बोलते रहो। So at the end of the day, you know that whatever factor, any factor which will help in the slow step would help the overall rate of the process. तो अगर कोई रिएक्टेंट, अगर न्यूक्लियोफाइल यहाँ पर स्लो स्टेप में काम नहीं करता है, अगर न्यूक्लियोफाइल यहाँ पे स्लो स्टेप में काम नहीं करता है, इसका मतलब है कि ये दो स्टेप का प्रोसेस है। इसका मतलब है कि ये दो स्टेप का प्रोसेस है। So from the kinetic studies, if I propose the mechanism of Sn1, don't you think it will look like this being the slow step, the rate determining step, where only the halide is involved? अरे हाँ ना बोलते रहो।
हाँ सर।
इसमें X- निकाल के ऐसा कार्बोकेटाइन बना दिया, and then I'll involve the nucleophile, say OH- here in the fast step, and obviously ये fast step में काम कर रहा है, इसलिए ये rate law expression में फीचर नहीं कर रहा है। बच्चे लोग हाँ ना बोलो. I repeat, something not featuring in the rate law expression, किसी के ऊपर में अगर रेट डिपेंड नहीं करता है, इसका मतलब है कि वो स्लो स्टेप में काम नहीं करता. यू आर गेटिंग मी? तो अगर मेरे को इसका काइनेटिक्स को एक्सप्लेन करना है, आई मीन इट्स सिंपल एज इट साउंड्स. You will not want to carry too much of baggage in your mind, and in due course, every mechanism should be understood from first principle. I think I'm not telling you something which is very hard to understand. The basic fact is, अगर कोई reactant rate law expression में नहीं है, मतलब वो स्लो स्टेप में काम नहीं कर रहा है. और अगर ये स्लो स्टेप में काम नहीं कर रहा है, फास्ट स्टेप में काम कर रहा है, इसका मतलब ये कि 2 स्टेप का प्रोसेस है. एक स्लो जिसमें सिर्फ हैलाइड है, एंड द न्यूक्लियोफाइल इज देयर इन द फास्ट स्टेप. यस और नो?
Yes, sir.
Naturally via a carbocation. Naturally via a carbocation. And then how would I propose the mechanism of Sn2? How do I propose the mechanism of Sn2? When it comes to the mechanism of Sn2, when it comes to the mechanism of Sn2, when it comes to the mechanism of Sn2, I'll be using this part of the board. And I have to keep both of them. I have to keep both of them in the rate law expression. What I'll propose is, it's a single step process. It's a single step process जहां पे ये OH माइनस आ रहा है, X माइनस जा रहा है. एक स्टेप का ही प्रोसेस है, यही स्लो स्टेप है, यही डिटरमाइनिंग स्टेप है. और इसलिए दोनों के ऊपर में रेट डिपेंड करता है. मेकिंग एंड ब्रेकिंग ऑफ बॉन्ड इज हैपनिंग इन द सेम स्टेप. This is what is called concerted. Making and breaking of bond happens in the same step. So Sn means nucleophilic substitution. Generally, people have a tough time in organic chemistry because you don't want to understand the basics more than the reagent and the product and the number of reactions you mug up or come across. Ideally, you will want to know the nature of the reactions first. So the moment I tell you hydrolysis of halide, a halide becoming alcohol, you find H minus going out, OH minus coming in, you will want to be very comfortable with the term nucleophilic substitution. एक न्यूक्लियोफाइल आया, दूसरा न्यूक्लियोफाइल चला गया. Substitution, you understand. And the two mechanisms, Sn1, Sn2, are absolutely kinetics drawn. So there could be a hydrolysis where rate law expression would suggest me this, and there could be a process where I'll have a kinetic study of this kind. Every time I have this kind of kinetic study, to justify this, I'll have to keep OH minus out of the slow step. And I have to keep nucleophile out of the slow step, means I have to keep it a two-step process where the slow step will have only halide and not nucleophile, and the nucleophile will feature in the fast step. Naturally, to do that, I'll make it a two-step process involving a carbocationic intermediate. And Sn2, where the rate is a function of both of them, इसके साथ भी order 1 है, इसके साथ में भी order 1 है. To keep both of them in the slow step, I'll have to have it as a one-step process, जहां पर making and breaking of bond is happening in the same step. And I think this should come very naturally to you. Sn1, Sn2. I think I have explained you the symbolic representation, why they are represented as 1 and 2, the unimolecular or bimolecular nature of the rate kinetics, and we are proposing the corresponding mechanism. Trust me, we are going to travel some distance and we are going to authenticate and prove everything which I have proposed so far. We want to move on. बच्चों लोग हाँ ना बोलो. Can I remove this clutter? Now, instead of talking about Sn1 and Sn2 separately, and you also understand that these might be two competing mechanisms. It's like to complete a process, you have two different pathways. If you have two different pathways, choosing one or something facilitating one would naturally be a deterrent to another. So Sn1, Sn2 would be largely taken as two competing mechanisms. And as I told you, instead of taking them separately and then talking about the similarities and differences, we'll rather want to have right away a comparative analysis of the two. I'll give you enough time to copy all of it, but right away, when I discriminate between Sn1 and Sn2, or basically when I compare Sn1 and Sn2, stuff like rate proportional to Rx only and rate proportional to Rx along with the nucleophile is where the story begins. You getting me? Everything starting from the symbolic representation to the terminology to the mechanism. I repeat, it's all going to come from the rate flow expression and the kinetic studies to begin with. And then, naturally, if I propose this happens in the slow step and this happens in the fast step, I propose it to be a two-step process. I propose it to be a two-step process with a carbocation intermediate. With a carbocation intermediate. When it comes to Sn2, so many times and trust me, y की जगह मैं nu ही लिखता हूं. It will be a one-step process. It will be a one-step process. And every time you don't have an intermediate, you propose it to have come from a transitory state. You know what is transitory state? You know what is transitory state? Transitory state is more of the picture which tells you how the progress would have happened. You know, you propose the making and breaking of bond happening in the same step. You propose the making and breaking of bond happening in the same step. You know, at the molecular level, you end up saying the amount of energy required to break this bond is going to come out of the energy released when this bond is being made. And if it's all happening simultaneously in a concerted step, एक step का process है तो intermediate तो हो नहीं सकता. Intermediate जो होता है कार्बोकैटायन हो कार्बन आयन हो जो भी intermediate होता है उसको हम लोग ऑथेंटिकेट कर सकते हैं, जस्टिफाई कर सकते हैं, कोई कोई केस में आइसोलेट भी कर सकते हैं, बट इट्स एग्जिस्टेंस कुड बी प्रूव्ड. A transitory state and its existence could be proved so many times, it could be isolated as well. Transitory state, on the other hand, is completely hypothetical. It's basically, as I tell you, the picture of how things would have moved. And a very popular representation of the transitory state in Sn2 is, you know, I do tell you, you'll want to draw these dotted lines. And the continuous bonds are the ones which are not affected, and the discontinuous bond is the one which is being made or broken simultaneously. So every time I draw a transitory state, I tell you that the bonds which are about to be made or about to be broken. That is how you draw a transitory state. And every time I draw a transitory state, I'm going to come up with the same choice of words. What is a transitory state? A transitory state, and you draw it in a manner that the bonds which are about to be made or about to be broken are shown within dotted lines or discontinuously. A carbocation or any intermediate, an intermediate could be proved, worked upon, in some cases isolated. Transitory state is completely hypothetical in the sense it's only going to tell you about, I repeat, how reactant would have matured to product, but it's also going to have its own advantages in the sense it's going to explain certain aspects of the corresponding mechanism. But I think so far so good. I think you're understanding me so far. यहाँ पर
Yes.
कार्बोकैटायन बनता है, यहाँ पर कार्बोकैटायन बनता है, और कार्बोकैटायन ज्यादा स्टेबल होगा तो प्रोसेस ज्यादा इजीली होगा, फास्ट होगा, बेटर होगा, यील्ड ज्यादा होगा, reactivity will be more, proclivity towards this mechanism will be more. if the corresponding intermediate is more stable. So suppose if I tell you that generally benzylic allylic more than 3 degree, more than 2 degree, more than 1 degree, naturally more than methyl, if the reactivity towards Sn1, certainly it's going to come out of the stability order of carbocation. You know the same is the order of stability of carbocation. Yes or no? Yes or no? A more stable carbocation, a more stable carbocation.
हाँ सर.
Benzylic allylic is pretty stable. 3 degree more than 2 degree more than 1 degree is the order of stability of carbocation. I think you all remember this.
Yes, sir.
So it was not surprising. It was not surprising that the example which I took and the example you'll find in all the textbooks in Sn1, chances are they're going to begin with tertiary butyl chloride only, which is a 3 degree carbon. And again, in case of Sn2, you see 1 degree more than 2 degree more than 3 degree will be the order of reactivity. क्योंकि यहाँ पर when you look at the transitory state, transitory state में ना कार्बन का 5 हाथ है. In the transitory state, you need to have a pentavalent carbon. And don't you think for carbon to have 5 bonds around it, and for the steric ease of formation of transitory state, these groups should be as small as possible. So again, it was not surprising that the example which I took was of methyl chloride, where all the 3 were hydrogen. Yes or no? Transitory state में कार्बन का 5 हाथ बनता है. The challenge is steric, और ट्रांजिटरी स्टेट आसानी से स्टेरिकली बनने के लिए you will want कि ग्रुप जितना छोटा हो उतना अच्छा है. The example which I took, or the example you will find in most of the books to begin with, is going to be methyl, because in that case all the 3 groups are hydrogen. And 1 degree में सबसे बेस्ट होगा, because 1 degree में the crowding will be lesser than that of 2 degree, जिसमें crowding will be lesser than that of 3 degree. Eventually will confirm कि 3 degree में हमेशा Sn1 ही होता है, और 1 degree में हमेशा Sn2 ही होता है. 2 degree में maybe Sn1 and Sn2 will compete. And in due course, there are going to be 4 factors. In due course, there are going to be 4 factors. One would be the structure of the halide. ऐसा नहीं कि सिर्फ halide पे nucleophilic substitution होता है, but halides are the best example for the study, and they are going to have the maximum reactions because halides are the best leaving groups. This would be the first criteria, and you can see this is what I've already looped in. Because right now, if I say 3 degree में Sn1 का chances maximum होता है, और Sn1 में 1 degree में Sn2 का chances maximum होता है, the criteria I'm exploring is the structure of the halide. वो अलग बात है कि यहाँ पर it would be about the stability of the carbocation. So here the justification is electronic in nature, and यहाँ पर 1 degree में the formation of transitory state would be the easiest, and the justification is steric in nature. And this is the language they'll want you to use, and this is the information they'll want you to have to begin with. So when I say Sn1 or Sn2, the first factor, the first criteria would be the structure of the halide. The second factor could be the nature of the nucleophile. Third factor could be the nature of the solvent or medium. And the fourth factor could be the nature of the leaving group. But by and large, factor 1 and factor 2 would have a more crucial role to play. 1, 2, 3, 4 is also the sequence in which they'll affect the chances of either Sn1 or Sn2. 1 or 2 are going to be the 2 important factors, जहां पर हम लोग Sn1, Sn2 almost decide कर लेंगे. 3 and 4 could be at most facilitating in nature. So for Sn1 or for Sn2, you will want to prefer one medium over the other. But by and large, 1 and 2 will decide whether a process is going to be Sn1 or Sn2. So I think I've made a few things clearer in the sense. I began with tertiary butyl chloride. I'm telling you about the stability of carbocation. Stability of carbocation in terms of more plus I effect, more hyperconjugative hydrogen, 3 degree being very stable, and this carbocation being very stable. I'm calling them electronic factors. And a compound like tertiary butyl chloride or a 3 degree halide will have more reasons to take up this mechanism, because here a stable carbocation would mean a more seamless, stable, low energy journey. Yes or no? Whereas in 1 degree, first of all, the carbocation is not very stable. Yes or no? And then in 1 degree, it's the easiest to form the transitory state. At the end of everything, if I tell you that maybe Sn2 has an edge over Sn1, I mean, if I look at the complete, spectrum of reactions, chances are there will be more Sn2 reactions than Sn1 reactions in general. You're getting me? In Sn1, the stability of carbocation, and in Sn2, the steric ease of formation of transitory state, and certainly the structure of halide would be the first deciding factor. Maybe in 3 degree हमेशा Sn1 ही होगा, 1 degree में शायद हमेशा Sn2 ही होगा. जितना कम ब्रांचिंग होगा उतना ट्रांजिटरी स्टेट बनाना आसान होगा. यहां पर हम लोग स्टेरिक फैक्टर का बात करते हैं, वहां पे हम लोग इलेक्ट्रॉनिक फैक्टर का बात करते हैं. दिस इज द लैंग्वेज विच यू वांट टू नो कि यहां पर इट्स अबाउट द स्टेबिलिटी ऑफ कार्बोकेटाइन प्लस आई इफेक्ट हाइड्रोकॉन्जुगेशन. एक बात याद रखना कि यहां पर एलाइलिक बेंजाइलिक लेकिन Sn2 को हर्ट नहीं करता है. एलाइलिक बेंजाइलिक में Sn1 अच्छा होता है, पर यहां पर एलाइलिक बेंजाइलिक में इन जनरल एलाइलिक बेंजाइलिक में Sn2 भी अच्छा ही होता है. ऐसा नहीं है कि हर बार दे विल बी कंपीटिंग. एलाइलिक बेंजाइलिक होता क्या है? एलाइलिक बेंजाइलिक होता है नेक्स्ट टू अ डबल बॉन्ड, नेक्स्ट टू अ रिंग. Next to a double bond or next to a ring would be about bringing a two-dimensional aspect to the carbon which is having the leaving group जिसके ऊपर में रिएक्शन हो रहा है, न्यूक्लियोफाइल अटैक कर रहा है. एलाइलिक में वो कार्बन sp2 होगा, रिंग में भी वो कार्बन sp2 होगा, टू डिमेंशनल होगा. टू डिमेंशनल नेचर और प्लेनैरिटी is always going to decrease crowding. Yes or no? तो एलाइलिक बेंजाइलिक में Sn1 में भी अच्छा होता है, Sn2 भी अच्छा होता है. Maybe in allylic or benzylic, factor 2 will become a bigger factor, the nature of the nucleophile. But 3 degree more than 2 degree more than 1 degree, and 1 degree more than 2 degree more than 3 degrees in Sn1 and Sn2 respectively need to be justified or explained on electronic grounds and steric grounds respectively. Am I clear on this part? 3 डिग्री सबसे अच्छा क्यों होता है Sn1? बिकॉज स्टेबल कार्बोकेटाइन नंबर. 1 डिग्री सबसे अच्छा Sn2 क्यों होता है? बिकॉज ट्रांजिटरी स्टेट बनना आसान होता है. यस और नो? 3 डिग्री मुश्किल होगा और यहाँ पर 1 डिग्री का कार्बोकेटाइन स्टेबल नहीं होगा. पीपल ऑनलाइन हाँ ना बोलो.
हाँ सर.
प्लीज हियर मी आउट. ये लिटरेचर है, ये थ्योरी है. And naturally, people can take liberty. What I'm telling you is the most common and the most student friendly, exam friendly approach, which needs to be instilled in the beginning. But you come across different authors, and as I told you, when it comes to the mechanism of organic chemistry, see, this transition is so wonderful that a man of physical chemistry gets a Nobel Prize for proposing a mechanism in organic chemistry. And naturally, the mechanism of organic chemistry has come from the study of rate kinetics, which is very much a part of physical chemistry. So Sn1, Sn2, even E2, these terms are given by a man who largely dealt with, physical things. And as I told you, we'll not want to go to the level where the people, who invented were, men of amazing acumen and intelligence. But an author can take liberty. An author can take liberty. You read a textbook of organic chemistry, and maybe a person would try to justify this sterically. ये sp3 से sp2 बनता है. जब कार्बोटाइन बनता है तो sp3 से sp2 बनता है. sp3 में बॉन्ड एंगल एक्सपेक्टेड होता है 109 डिग्री 28 मिनट्स और sp2 में बॉन्ड एंगल एक्सपेक्टेड होता है 120 डिग्री. sp3 is three dimensional, sp2 is two dimensional planar. Yes or no? So sp3 से sp2 expected 109 to expected 120, three dimensional to two dimensional. Don't you think sp3 to sp2 is like lesser crowding? Is also like carbon being able to outstretch its arms? Yes or no? And this relief from crowding, this tendency to attain Sn2, sp2 nature from sp3, this relief from crowding and this relief which it will gain by outstretching its arms from going sp2 from sp3, don't you think this desire or this requirement will be maximum in the one which is maximum crowded? So can I say the tendency to go to a sp2 planar structure could be sterically explained in a compound which is sterically the most crowded? You're getting me? But these are statements that you'll very, very rarely find in exams at your level. So at your level, the questions would be like 3 degree में Sn1 होता है because 3 degree कार्बोटाइन सबसे stable होता है. But trust me, on a given day, in a given exam, if you find a statement like in 3 degree halide, because of maximum steric crowding, the desire to attain the steric relief by moving to sp2 carbocation is the maximum. And this steric factors is the driving force for 3 degree being most reactive towards Sn1. And that is also going to be a true statement. Yes or no? So although it's going to be electronically explained in all of class 11, 12, all of, the exams you're going to come up with, but there could be a steric explanation to this as well. Similarly, यहाँ पर हमारा काम steric factor से चल जाता है. 1 डिग्री में सबसे अच्छा होता है बिकॉज 1 डिग्री में ब्रांचिंग सबसे कम होगा, ट्रांजिटिव स्टेट बनाना सबसे आसान होगा जहां पे कार्बन का पास है. ठीक है? But I've told you in the past, even if breaking of bond and making of bond happens in the same step, breaking has to initiate a little earlier. थोड़ा जगह खाली होगा तभी तो आगे अटैक करेगा. थोड़ा जगह खाली होगा तभी तो आगे अटैक करेगा. Yes or no? So momentarily, breaking will precede making. And even momentarily, if you believe that there's going to be some positive charge, now this positive charge is good for Sn2. This positive charge is good for Sn2. One basic difference between Sn1 and Sn2 is Sn1 में the nucleophile is willing to wait. Slow step हो जाए फिर nucleophile जाएगा. Sn2 में क्या होता है? Nucleophile goes right away in the first step. Remember I tell you, nucleophilicity is a kinetic term. Basicity is a thermodynamic term. So a strong nucleophile is the one which is faster. So can I say, with a nucleophile being more nucleophilic, chances of Sn2 will grow because there the nucleophile is less nucleophilic. It's laid back. यहाँ पे न्यूक्लियोफाइल तुरंत जाके अटैक करते हैं, एक स्टेप नहीं खत्म होता तो सारा खेला. Yes or no? Now don't you think if this positive is more, It's more inviting for the nucleophile. This positive charge could increase the nucleophilicity of the nucleophile. And later on, I'll tell you about solvent as well. The nature of solvent could also play a role. But so far we're talking only about the nature of the halide. We're limiting it to the branching, the structure of the halide. And don't you think if there is more branching, with more plus I, more hyperconjugation, this positive will not grow enough. And if this positive is substantial, it's good for Sn2. How do I talk about this positive? I talk about this positive because I know even if making and breaking is happening in the same step, the breaking of the bond starts momentarily earlier. And whatever little positive charge is there because of the bond, starting to break earlier than the new bond being made, this positive would be inviting for a nucleophile, and this positive will be substantial and of the order of higher magnitude if the halide is 1 degree more than 2 degree more than 3 degree. You're getting me? So I can associate an electronic factor here, and I can associate a steric factor there. And it's not me talking this language. This is something which you'll find in, the so-called more liberal books on organic chemistry. So as I do tell you, an author can take liberty. An author can, assign his or her own way of, looking at the mechanism of Sn1 Sn2. 11-12 में मैक्सिमम टाइम्स यहाँ पर हम लोग इलेक्ट्रॉनिक फैक्टर लगाते हैं, कार्बोकेटाइन का स्टेबिलिटी का बात करते हैं, ज्यादा ब्रांचिंग, ज्यादा स्टेबल कार्बोकेटाइन, इलेक्ट्रॉनिक फैक्टर. बट इन ड्यू कोर्स इफ यू कम अक्रॉस अ क्वेश्चन ऑफ द काइंड sp3 से sp2 होने में इसको स्टेरिक रिलीफ सबसे ज्यादा मिलता है, और उस स्टेरिक रिलीफ का रिक्वायरमेंट सबसे ज्यादा 3 डिग्री में होता है जहां क्राउडिंग सबसे ज्यादा है. दैट विल आल्सो बी अ राइट स्टेटमेंट and would be like a good information, a good knowledge to have. Similarly, 1 degree more than 2 degree more than 3 degree, जितना कम ब्रांचिंग उतना फंड से ट्रांजिटरी स्टेट बनेगा. स्टेरिक फैक्टर इज ऑल वेरी वेरी क्लिशे बाय नाउ. एकदम रूटीन चीज है. जितना छोटा, जितना कम ब्रांचिंग, मिथाइल में हम लोग एग्जांपल देते हैं, उतना फंड से ट्रांजिटरी स्टेट बनता है स्टेरिक फैक्टर. But yet again, in a given statement, if they talk about this positive charge would be inviting for this nucleophile, and this positive charge, if at all, will have its say if there is less branching, which would be the best in 1 degree, would be like bringing an electronic factor to Sn2, and that is also going to be pretty good, pretty right. You're getting me? आगे बढ़ते हैं. 3 degree more than 2 degree more than 1 degree, 1 degree more than 2 degree more than 3 degree, 3 degree में हमेशा Sn1 ही होता है, 1 degree में हमेशा Sn2 ही होता है, 2 डिग्री में थोड़ा झगड़ा होगा और बाकी फैक्टर्स का इंपॉर्टेंस बढ़ जाएगा. बेंजाइलिक क्लैरिक यहाँ पर अच्छा होता है, बेंजाइलिक क्लैरिक वहां पर भी खराब नहीं. ठीक है? अरे हाँ ना
Yes, sir.
Now we'll explore more factors. अभी पास हुआ ना? पास हुआ तो अरे बोलता ही नहीं है कोई यार. There will be factors which will be common. Let's take up some common factors. Like benzylic allylic, I told you is a common factor. Let's take up a factor like vinylic arylic halides are very less reactive. Now this is for both Sn1 and Sn2. Vinylic and arylic halides are very less reactive both for Sn1 and Sn2. हेलो हेलो बेटा पढ़ा रहा हूँ, बेटा पढ़ाने दे बेटा. पढ़ाने को वीडियो कॉल नहीं हो सकता अभी. सर कॉपी हो गया था ना ये वाला. तो फैक्टर लाइक विनाइलिक, विनाइलिक मतलब डबल बॉन्ड वाला, अराइलिक मतलब रिंग वाला. विनाइलिक और अराइलिक, विनाइलिक और अराइलिक, विनाइलिक और अराइलिक दोनों में कम रिएक्टिव होगा. बिकॉज ये तो मैं जीओसी में पढ़ाता हूँ, कार्बोकेटाइन का स्टेबिलिटी के बाद सीधा पढ़ाता हूँ, पहला क्लास में पढ़ाता हूँ मैं ये. When I talk about stability of carbocation, the next thing I tell you about is reactivity of halides. यहाँ पे डबल बॉन्ड कैरेक्टर होगा ना, यहाँ पे डबल बॉन्ड कैरेक्टर होगा, तो बच्चे लोग हाँ ना बोलो, यहाँ पर डबल बॉन्ड कैरेक्टर होगा, डबल बॉन्ड डी बी सी, यहाँ पर डबल बॉन्ड कैरेक्टर होगा, फिर हाँ नहीं बोलते हो। डबल बॉन्ड कैरेक्टर होने से बॉन्ड को तोड़ना मुश्किल है, तो विनाइलिक और एनालिक दोनों में कम रिएक्टिव होगा, विनाइलिक और एनालिक दोनों में कम रिएक्टिव होगा। यस और नो?
हाँ सर।
ब्रिज हेड पे अगर एक हाइड्रोजन लगा है, if there is attached to a bridge head, you know bridge head, if you have a halide where the halogen is attached to, if you have a halide where the halogen is attached to the bridge head carbon, you know bridge head carbon, a bicyclo compound where these two are called bridge heads. I would have told you about this in nomenclature. These two are called the bridge heads. How do you identify a bridge head? A bridge head would be the point where you find three different branches originating or culminating. जहां से लगेगा कि तीनों ब्रांच निकल रहा है या कल्मिनेट कर रहा है, उसको बोलते हैं लोग ब्रिज हेड। ब्रिज हेड कार्बन पर पॉजिटिव चार्ज स्टेबल नहीं होता है, बोलते हैं ब्रेड्स रूल। ना तो पॉजिटिव स्टेबल होता है, ना नेगेटिव स्टेबल होता है, ना पाई बॉन्ड स्टेबल होता है, तो यहाँ पर कार्बोकेटाइन फॉर्मेशन इज रूल्ड आउट। और पीछे में इतना बड़ा केज जैसा बना हुआ है, कहां से Sn2 होगा? Sn2 के लिए दिस वुड गो आउट एंड दिस वुड कम इन द सेम स्टेप। Sn2 में इसका जाना और न्यूक्लियोफाइल का आना एक ही स्टेप में होना चाहिए। यस और नो? तो इसमें कार्बोकेटाइन इज नॉट पॉसिबल, कार्बोकेटाइन cannot be formed, which is Brett's rule, and there will be a steric hindrance to Sn2. Yes or no? So halide where the halogen is attached to the bridge head carbon is also very less reactive towards both Sn1 as well as Sn2. बता दूं बच्चे लोग? So I told you, we are basically talking about comparison. There will be some similarities and more differences. More differences because they would look like two competing mechanisms altogether. But certain factors would be common. Like arylic benzoic will be more reactive and vinylic chloride will be less reactive. And a bridgehead carbon halide would be a bad substrate for both Sn1 and Sn2. Pretty much on these lines. I did tell you this at the onset as well. Iodide more than bromide, more than fluoride. Fluoride हम लोग फॉर्मेलिटी के लिए लिख लेते हैं, is the order of reactivity again towards both Sn1 Sn2. मैं ना ये सब के बारे में और बात करूंगा when we mature a bit more. But do you remember me telling you a little bit of primary kinetic isotopic effect in aromatic nucleophilic electrophilic substitution? CH3CH6 is equal to C6D6 is equal to C6T6 Philotrap reaction नाइट्रेशन थोड़ा बहुत बताया था ना, याद नहीं है वो अलग बात है यार। But the rule of the game is a difference in bond energy. A difference in bond energy will reflect in reactivity. See, so many times reactivity could be about the rate of the process as well. When I say reactivity, it's a little open-ended. It could be about rate as well as yield, or both. In this case, both. a difference in bond energy will be reflected in a difference in rate only if that bond is broken in the slow step. Only if that bond is broken in the slow step. You see Sn1 Sn2 ये वाला बॉन्ड तो दोनों में स्लो में टूटता है ना. कार्बन हाइड्रोजन का बॉन्ड तो दोनों में स्लो में टूटता है. Sn2 में तो एक ही स्टेप होता है और Sn1 में यही टूटता है स्लो स्टेप में. यस और नो? हेलो. Yes, please tell me. Okay. Okay. আমি পড়াই এখনো পড়াচ্ছি. আমি এখনো ক্লাসে আছি. ছেলের নাম কি? আচ্ছা মিস্টার দা, ক্যান আই কল ইউ ইন এন আওয়ার? আমি একটু এখন একটা অনলাইন ক্লাসে আছি. I'll call you back. I'll call you back in an hour. Now beta carbonyl. You understand alpha beta? So if this is the leaving group, X is the most common representation of a halide. So many times I write L here, which will mean it's the leaving group. जिस कार्बन चलेगा उसको अल्फा कार्बन बोलते हैं, जिसका नेक्स्ट वाला कार्बन को बोलते हैं बीटा कार्बन. ये इंपॉर्टेंट फैक्टर, ये तुमको नॉर्मल हर किताब में नहीं मिलेगा. ये भी रिसेंटली जेई में आ रहा है, ध्यान से सुनिए. A beta carbonyl will facilitate Sn2 and inhibit Sn1. A beta carbonyl will facilitate Sn2 and will inhibit Sn1. Know it. First of all, know it. I mean, you would be given a compound like CH3Cl, and you would be given a compound like CH3C double bond O CH2Cl. If you don't know about this, it would be very, very unlikely that you would believe that this will have a higher Sn2. You know, that would look like a very bigger compound, and this would look like a small little methyl chloride. जिसमें Sn2 हमेशा पढ़ते हो. Yes or no? But when you look closely, it's the same methyl chloride with a beta carbon. You're getting me? अरे हाँ ना बोलो. अदरवाइज क्या ना, अदरवाइज ये मिथाइल क्लोराइड देखते समझ में आएगा सबसे छोटा तो यही है, इसमें बेस्ट Sn2 होता है, यही हमेशा देखते हैं, हर किताब में लिखा रहता है. पर अगर ये दोनों को कंपेयर करना है तो उसमें Sn2 अच्छा होगा, बेटर होगा, फास्टर होगा, क्योंकि इट इज लाइक उसमें बीटा कार्बोनिल लगा दिया है. समझ में आ रहा है मेरा बात? अब बीटा कार्बोनिल करता क्या है? बीटा कार्बोनिल करता क्या है? ये बॉन्ड हमेशा पोलर रहता है. ठीक है, ये बॉन्ड हमेशा पोलर रहता है. मेसोमेरिक इफेक्ट, रेजोनेंस. अब ये जो पॉजिटिव है, मैं क्या बोलता हूं, ये बॉन्ड टूटना चालू हो जाएगा, यहाँ पर थोड़ा सा नेगेटिव होगा, यहाँ पर थोड़ा सा पॉजिटिव होगा, इसको आकर के इसके ऊपर में अटैक करता है Sn2 के लिए. यस और नो? अब ये बॉन्ड तो पोलर है, अब ये जो पॉजिटिव चार्ज है ठीक नेक्स्ट कार्बन पर, इट विल हैव अ सिनर्जिक इफेक्ट. This will attract the nucleophile. So this positive is more attracting or more inviting for the nucleophile. And trust me, कोई भी फैक्टर जो न्यूक्लियोफाइल को अपनी तरफ खींचता है वो उसका न्यूक्लियोफिलिसिटी बढ़ाता है और Sn2 का चांसेस बढ़ाता है. You getting me? ठीक है, तो ये बॉन्ड हमेशा पोलर रहता है. रिमेंबर परमानेंट इफेक्ट, इंडक्टिव इफेक्ट, रेजोनेंस, दिस बॉन्ड इज ऑलवेज पोलर. तो ये जो पॉजिटिव चार्ज है, ये न्यूक्लियोफाइल को खींचने में, अट्रैक्ट करने में, इनवाइट करने में इट वुड एड, एंड दिस विल नेचुरली thereby, as I told you, facilitate Sn2. इसमें अगर Sn1 होता इफ और X माइनस चला जाता तो ऐसा कार्बोकेटाइन बनता। Sn1 में तो कार्बोकेटाइन बनता और ये बॉन्ड पोलर है तो पॉजिटिव पॉजिटिव तो रिपेल करता है ना, तो बहुत बड़ा प्रॉब्लम है। So this repulsion will inhibit Sn1. So if there is a beta carbonyl present, Sn2 will be promoted, Sn1 would be inhibited. Presence of a beta carbonyl group would promote Sn2, would inhibit Sn1. ठीक है, ये सब थोड़ा नया नया चीज है, इसको जान लो, ये सब रूटीन नहीं है, ये भी एक इंपॉर्टेंट फैक्टर है। अगर मान लो ऐसा एक लीविंग ग्रुप है, अगर ऐसा एक लीविंग ग्रुप है और इसके बगल में ऑक्सीजन जैसा है कुछ, जिसके पास लोन पेयर है, ऑक्सीजन है, नाइट्रोजन है, ऐसा कुछ है, नाउ दिस इज मोर रिएक्टिव फॉर बोथ Sn1 Sn2। ये Sn1 Sn2 दोनों के लिए ज्यादा रिएक्टिव है, ठीक है। ऑक्सीजन हो नाइट्रोजन हो, दो भी हो, लोन पेयर जैसा होगा, Sn1 Sn2 दोनों को फेवर करता है, Sn1 Sn2 दोनों को फेवर करता है, Sn1 Sn2 दोनों को फेवर, ठीक है। rub it off। नेचुरली यहाँ पर कार्बोकेटाइन बनता है, यहाँ पर कार्बोकेटाइन बनता है, Sn1 में कार्बोकेटाइन बनता है, कार्बोकेटाइन फॉर्म, so you'll have molecular rearrangements, so hydride, methyl, phenyl स्टेफ और रिंग आंसर ये सब होगा। यहाँ पर कार्बोकेटाइन बनता है तो हाइड्राइड स्टेफ, मिथाइल स्टेफ, रिंग एक्सपेंशन ये सब होगा। Sn2 में कार्बोकेटाइन नहीं बनता है, Sn2 में कार्बोकेटाइन नहीं बनता है, so there is no rearrangement, ठीक है। रीअरेंजमेंट होगा कि नहीं होगा, इस कार्बन पे जाएगा तो उस कार्बन पे जाएगा। मैं पहले भी बोलता था, इसको बोलते हैं रीजियोकेमिस्ट्री, इसको बोलते हैं रीजियोकेमिस्ट्री। इस कार्बन पे जाएगा कि इस कार्बन पे जाएगा, विच रीजन ऑफ द मॉलिक्यूल विल गेट अफेक्टेड, मॉलिक्यूलर रीअरेंजमेंट होगा कि नहीं होगा। और सो फार आई टोल्ड यू मॉलिक्यूलर रीअरेंजमेंट इज पॉसिबल ओनली इफ देयर आर कार्बोकेटाइन। Regiochemistry. Let's take up a difference in stereochemistry as well. I doubt how many of you have done Sn1, Sn2 in detail, and it's not like I'm going to impart complete wisdom in today's class only. So maybe I would jot down some points, some factors which you'll want to come a little prepared with, and maybe we'll carry on with the same discussion in tomorrow's class as well. I think it's better to spread it over 2 particular days, and also give you a little time to read a bit on Sn1, Sn2. But stereochemistry is about, say, a corresponding special projection. When I make this ABC, it becomes chiral. Who will tell me what happens in Sn1? Suppose in Sn1 I treat this with y minus, Sn1 हो रहा है naturally Sn1 के रूप में, क्या होगा बोलो? Anyone? Any idea? Do you remember this fact? 4 different drugs and this will be optically active. It's called a chiral carbon. It could be dextrorotatory or levorotatory. You remember that part? When this is subjected to an Sn1, when this is subjected to an Sn1, you'll have something like this as well as something like this. I mean, if I say this, a case of optical retention, and if I call this a case of optical inversion, do you relate to these terms, retention and inversion? Please have a look and tell me. So retention and inversion would bear pretty much their literal meaning. Retention and inversion would bear pretty much their relevant literal meaning. तो जैसा है उसके जैसा ही स्ट्रक्चर अगर आता है, जैसा है उसके जैसे ही अगर स्ट्रक्चर आता है, तो हम लोग बोलेंगे रिटेंशन हो रहा है, ऑप्टिकल रिटेंशन हो रहा है. और अगर उसका मिरर इमेज जैसा आता है, उसका मिरर इमेज जैसा आता है, तो हम लोग बोलते हैं इन्वर्सन हो रहा है. अगर ये दोनों बराबर बराबर बनता है, द टू आर कॉल्ड इनैंसियोमर्स, और अगर ये दोनों बराबर बराबर बनता है, then it's called a racemic mixture. It's called a racemic mixture. Remember that? No optical activity because of external compensation. आप राइट में लिखाएगा, हाई लेफ्ट में चलेगा, है ना? आधे इधर जाओ, आधे उधर जाओ, है ना? चलो यार, तो मेरे को लगता है ना इसके ऊपर में बहुत थोड़ा सा काम करने का जरूरत है. रिटेंशन इन्वर्सन अगर दोनों ही होता है, then Sn1 leads to what's called racemization. Sn1 leads to racemization, although the racemization would be not 100%. ये 100% racemization क्यों नहीं होता है, दोनों बराबर क्यों नहीं बनता है, क्या होता है, is something which I want you to know a little more before I take it up in details. And what will happen in Sn2 is, what will happen in Sn2 is, if this is chiral, and tell me how you can prove it, there will be 100% optical inversion. Obviously, while doing all of it in compounds involving a 6-membered ring, I'll need to tell you a little bit about the conformational isomers, a little more than what we would have done in the past in terms of staggered eclipse. I did a bit of staggered eclipse with you using the so-called Newman projection. So, we would stretch that to the shear form of 6-membered ring. And there's a lot of stereochemistry which, would be required when we take up the stereochemistry of the nucleophilic substitution mechanism. I see myself doing that in the upcoming classes, but as I told you, when it comes to Sn1 causes racemization and Sn2 causes inversion, this is absolutely routine. एकदम बच्चा वाला चीज है, हर किताब में लिखा हुआ है, हम तुमको किताब का नाम भी बता दिए हैं. And I hope you start reading about Sn1, Sn2 sooner than later. Because henceforth the discussions in the classroom need to be a little more mature, where your participation will play a larger role. So I think regiochemistry with a rearrangement possible here, because it's involving a carbocation, and no rearrangement there is also understood. And in terms of pressure projection, here in Sn1, you'll expect both retention and inversion to happen, although not equally. You'll want to explain this when I take it up next class, and again you'll have to prove optical optical inversion here, both the logistics and the manner in which we'll be able to prove it. Plus, and this is why I don't want to carry on for a longer period of time, because I find the people completely at loss, and it would make more sense if I address you once you have read a little bit more about Sn1, Sn2 from any particular source. So from point 12, point 13, I'll move to point 14, 15, 16, and I don't know exactly where am I going to end, but you need to come a little more prepared. Role of solvent. Something like a polar protic solvent. A polar protic solvent promoting Sn1 and a polar aprotic solvent promoting Sn2, and trust me, there's a long way to go. This is hardly the beginning. The nature of solvent, the nature of nucleophile, the nature of leaving group are things which we'll want to take up in the coming classes. And again, a lot of basics of Sn1, Sn2 will need multiples revisit, because expect the question paper to be full of a lot of questions here. These ideas would come handy. So I think we'll want to stop here for the time being, largely because I would want to give you a little more time to get more acquainted with the two mechanisms, and let's see each other in the next class. Fair enough? I think the stuff which we covered so far was not very difficult to understand, and as I do tell you, in due course, only if you are able to relate to the mechanism in one way or the other, and if it all starts falling into place and starts appearing very naturally, it would be an easier terrain to travel. It would be an easier thing to recall as well. You find something out of place, and you would want to object. But so far, I've kept it simple. I think I came up with the mechanism exactly on the lines of the proposed rate law expression. So you keep it simple. A lot of reading needs to be done. Come prepared with more on Sn1, Sn2. As I told you, it's going to be a very long term. Nucleophilic substitutions followed by elimination. Once I'm done with a lot of reaction mechanism, I see myself going into the trivia like methods of preparation and properties which we can do in a bit. So this much for the time being. Stay happy, stay healthy. See you people. मिलते हैं बच्चे लोग. Bye bye.
Bye, sir.
Bye.
Bye, sir.
Bye, बच्चे.